Hi, this is Junaid, Neurochemical Care Stroke and Epilepsy Specialist. Today I'll be presenting on artificial intelligence in neurology and update. I'm very grateful for Pakistan Society of Neurology, PINS, and Movement Disorder Society of Pakistan to invite me for this important update. This is a huge update, and therefore there will be a lot to talk about in this particular session. So what I've done is that I'll be recording this video and then throwing it on the web, and then the link is over here in the QR code, and also the link is down here as well, where you can actually go back, review, and re-review. Another thing is, unfortunately, I do speak a little fast. I've heard about it. I tried to slow down, but unfortunately it's not possible sometimes. So it would be best that you can pause, rewind, re-review some of the information that we have done. Other important thing is that that website will contain all the references with direct links, so you can easily go back and review the data from which this presentation was created from. So my disclosure is simple. I am a Vice President of Clinical Strategy at VeeOne Health, founder of AINeuroCare, executive team committee member of the PINS, and AI committee member of UPNA Merit. This particular talk is going to be divided into three parts. Number one is going to be just to demystify artificial intelligence in healthcare. There's a lot of myth that goes around it, and I wanted to make sure that people do understand what AI really means and what it entails as far as doing a machine learning project, which is an applicable form, especially in Pakistan, where there's a lot of talent, but unfortunately not a place where to put it. So this would be something that you can actually take with you to really understand what AI is all about and maybe start your own machine learning project. The second one would be to understand the general trends in artificial intelligence with specific examples in neurology. And then finally, I think we're going to talk about updates in neurology, and that might actually be online the most of the part. One of the key portions of it, analytics, will be discussed by Dr. Adil Maiman, which is my co-presenter, where he is taking his own machine learning project and give you applicable insights on why and what he's doing and for what reason. So that would be very important. Therefore, I'm going to cut myself a little short and also make sure that everything is available for your perusal in online format. So we talk about machine learning and artificial intelligence and deep learning in an interchangeable way. When we are talking about artificial intelligence, we are talking about deep learning. What is deep learning? Deep learning is basically a complete paradigm shift in software design, software computing, etc. What we have done is that we used to give instruction sets to the computer and say, you know what, if this then that, if this then that. There will be millions of codes of addition, subtractions, if this, that, etc. And you created a particular piece of software. What we have done is that now we don't give that. What we give is, here you go, here's the data. Here are a million pictures of cats and dogs. Figure it out. We don't want to give you an instruction set. What we want to give you is that here are the examples of a cat, here are the examples of a dog. Train yourself and find out in the next set of picture, is it a cat or a dog? So we are not training the computer. Data is training the computer. We are not writing the code. Data is writing the code. This is truly the software revolution that we are seeing in terms of artificial intelligence. So what is the real difference between statistics and machine learning? Look, when we were doing statistics, what we really wanted to know was the inference of the data relationships. What we wanted to find out, if the person actually had diabetes, hypertension, what is the risk of the stroke? What we are trying to do with machine learning is not just getting inference. What we really want to know is the prediction. We want to know that if I'm going to give you another patient after the million patients you have analyzed, what is the risk of that patient having a stroke itself? What is the prediction that you think that that particular patient will actually have a stroke? This is completely changing the paradigm. They are not exploring over here why. We just want to know who. And this is where the difference comes in. We are not trying to explain why things are correlating, inferring, etc. We don't care. We are just want to know what is the prediction of the next event. And that's where the real power comes in. Dude, this is like sitting on a blackjack table and finding the next card who's going to make me win the game. End of discussion. I'm making money over here. I don't want to know how you came up with the solution, how you came with this particular conclusion. I don't care. I just want to give you the massive amount of data. You analyze it and give me the prediction next. That is it. Prediction, prediction, prediction. Machine learning is simply when a company is actually concentrated on the core performance of things. I don't care about the variables, how they are significant in relation to each other. I just don't care about anything. I just want to know the results. And this is very truly game changing. Let me give you what a probable probabilistic predictions and models look like. So data is like an ingredient in cooking. For example, you want to make a bread. You take that data and you put it into algorithms, and you take these algorithms and then divide them into different algorithmic solutions in which you are able to bake that particular algorithm and then move it into a proper recipe, which is the model. These are different set of algorithms or set of competing algorithms, etc., that would change into a complete model. And once you have the model, when you have the recipe, then you get the bread, which is the prediction. So what we're looking for is the data converted into an algorithm with fine-tuned into a model, giving me a prediction that I want. So we are cooking predictions here. We are not doing anything else. That's where artificial intelligence lies. And the most important ingredient is basically data. Now, everyone talks about the importance of model, but believe it or not, data is the key thing. Data, data, data. Look, you talking about models is like talking about a car with a shiny rim and a tire, and you're forgetting to put the gas in. The AI models, literally, data is the gas for them. So if you're not going to put the gas in it, it's not going to function. It doesn't matter how shiny your freaking tires are. So it's very important that you understand the real importance of data. Data is basically the new oil, the complete new economy in which ExxonMobil in 1990s was at the top of it. Now we're changing it to Google, Facebook, Tesla, Uber, etc. And why is that? Because they own the data. The key thing that to understand is that even companies that are being seems like stupidly valued in terms of stock markets, even companies that are valued that seems completely ironic, has to understand the underlying value of them. For example, Tesla is not a car company. You do not value it as if it was Ford. You value it because it's a data company. It has 1.6 billion miles under automated driving, and that's where its true value lies in. So data actually converts into true value. Now, this is the most important paper that you have to read, and if you're reading a few papers, and this is from Google, and in which it actually goes into especially the high stakes AI. How do you define high stakes AI? High stakes AI that they define it actually into conversational and healthcare. Conversational AI is clearly because you do not see any result except what is going to be spoken to you through a virtual speaker, a virtual symptom checker, etc. So you do not have any other information that you can glance on a web search through your eyes. So at that point in time, the specificity of that conversational AI is extremely important. And healthcare, I don't need to tell you, it is limbs and lives at stake. So in these high stakes games, it is extremely important that the data work is very crucial because it has long-term impact on actual problem solving. And this actually goes into a complete detail how data work can translate into multiple issues. And we're going to tell you some examples in the movie that racial biases, confounding biases, data shift biases, model shift biases, all of them come because data work at its essence was not done better. And this is where the key lies. And therefore, data work is the most important work, especially in terms of high stakes AI. At the end of the day, in any situation, to be honest with you, healthcare or not, data is more important than the model itself. Because the minute you have the data, you can create new models. You can use new technologies, new forms of models, new forms of computing, edge computing, etc. into your current data set. So the minute you have a good, clean data set, that is the more perpetual source of value that you can ever have. Now, why do I say that? And let's come to the AutoML in a minute. But these are the general trends in artificial intelligence that we're looking at. Automated machine learning, MLOps, transfer learning, multimodal data, privacy, and collaboration. So let's start with automated ML. What is automated ML? So automated ML is, I told you that there are two really pathways. One is data turned into prediction, right? That's what the point is for the whole situation. I want to turn my data into actual prediction. So the data preparation and cleaning is there, and then eventually the model validation and selection, which will never be automated. But everything in between, feature selection, feature engineering, model building, model training, hyperparameter optimizations. For example, if you have to tune the hyperparameter, which particular parameter you're going to actually emphasize within that model, weight better, weigh less, etc. All this, the complete end-to-end of that particular problem is now automated. And to be honest with you, it reduces a significant amount of work. It reduces a significant amount of human interface that is needed. And to be honest with you, it saves a lot of money. If you go to Google Cloud, you can easily upload your data with a few clicks. With a few clicks, you can now, at this moment in time, create a completely generated machine learning project with their AutoML deciding feature selection, hyper optimization, characterization, etc. So it is very, very easy. And this has changed the way businesses are doing work, right? I mean, Uber knows which taxi to call next. Grocery stores now which to stock better. So all of these things are being done, and it has changed the way the business is being run, at least here in the United States. Because anytime you have data, you can turn it into very easily into a machine learning prediction model. So the next batch of flour, the next batch of utensils you have to order, you know exactly when, where, how, etc. So this has been applied to artificial intelligence. As a matter of fact, it has been applied into neurology. This is a prime example. An automated machine learning was applied in patients to predict brain age. But they did the cortical anatomical measures, and within the cortical anatomical measures, they were able to predict what the brain age is as compared to what their true age is. I mean, clearly we know that there's differences in patients which have dementia that can have decreased cortical anatomical measures, and we really want to know what their brain age is as compared to truly if they have dementia or not. This is extremely important, and as you can see, these studies are utilizing these newer methods into much easier form of creating machine learning projects and bringing it into clinical applications. The other big thing is that people with limited code experience, especially physicians, can actually apply these application models into different machine learning projects. And you do not need extensive experience in coding to actually utilize machine learning projects into your own clinical applications to develop new ones for market. So this is one of the papers in which OST and chest x-ray, both of them, OST is basically optical coherence tomography, which is ultrasound images, a very huge publicly available database is available, so is 50,000 chest x-rays. They just took that, gave it to a bunch of physicians who had no significant coding experience, and realized that they can do something good about it. And then eventually, when it has proper clinical application, proper value-driven situation, they can actually hire an artificial intelligence engineer and then go and commercialize that project. But it is not that hard. What is hard? Data. You have to make sure that you actually have the data, clean processed data. Coding itself is becoming less important with the new code-free or no-code approaches that are coming. As I said, complete code-free multimodal image classification has been used over here. Not only that, they actually compared Amazon, Apple, Google, different models itself and saw what their accuracy is. So not only can you actually just end up having a particular model that is trained, but you can actually find where you want to train the model and train it multiple places to see which one's better and compare F-scores on it. So this has completely revolutionized the way we do machine learning projects. Again, it is code-free, and not only that, we're able to train that, but we can deploy it at the edge. So smartphone is basically a device that you can actually have machine learning, new chips, all of them have it. Not only can you do that, you can actually also deploy that into a machine learning. So when you actually upload a new OCT image, the mobile phone can itself run the actual algorithm and give you the result. So the idea is that even that level of extension is possible, that you can have a code-free, completely automated ML system published into a cell phone. So clearly things have changed significantly, and you need to understand this particular trend in artificial intelligence. And again, it's clearly changing the way the business is run, and this is a Harvard Business Review article if you want to read more about it. Let's say if you do have coding issues, 27% of the papers that are published in artificial intelligence also include the code. So if I have to go and look at some of the papers, and if I can't find that code, I actually go to papers with code and actually find a similar study and look at the different models they have used, and maybe download that particular model from PyTorch and GitHub and then use it into my particular study, because those are open access, completely free, available algorithms that you can use. So again, there is a complete shift in actually model development, model work. It is more open access. It is more freely available. The issue remains to be more so with the data. The second big thing that's happening is transfer learning. Now, there are situations where you actually have insufficient data, or you have incomplete data, or you have data that needs to be further explored. What you can do is you can find a similar study in which the algorithm was trained. In that particular algorithm, when it was trained, you take that learning of that algorithm and apply it to your machine learning with limited data to find some predictions and see what's going on. Now, it sounds a little more complex, and it is, if in theory, and I would love to go into more detail, but let me just give you an example. So in the real world, what's been happening is, this is called the ImageNet, right? Dogs, cats, flowers, everything has been identified. Google can identify, Google Photos can identify. As a matter of fact, ImageNet is available for free, and you can upload your own database of images and it will classify for you. People do that all the time as far as classification is concerned, and you can see more and more this coming into, at the end of the day, on the edge devices and the mobile phones, where pictures are being able to identify human images, etc., etc. This transfer learning doesn't really truly apply to medicine, of course, right? Medical images are different. But here's the situation. If I had a medical image in which I have trained skin lesions or biopsies for, let's say, 1 million patients, and that was actually looking at a skin cancer, squamous cell carcinoma, it learned how to de-identify, edge identify, was able to say that what the staining was, and that algorithm now knows how to classify the particular images. Now, can I apply it same to the digital pathology of glioma? Yes, you can, right? I mean, that's what the real issue is, that how do you take that learning and transfer it to another learning? There are multiple ways and approaches to it. This is one of them, in which basically the person has identified a large amount of unlabeled, completely unlabeled, right? Nobody told me that this is where the cancer is. Nobody said, I'm not even giving example to the computer. I'm just saying, here are a lot of images, do whatever you want to do with it. At the very end step, at the very last step, where you have to fully connect the classification layer, then you train a very small amount of data. Then you introduce the very small amount of data and say, you know what? Oh, by the way, you did a very fantastic job because I didn't tell you what to do, but here's what I was looking for. And then you actually retrain that training model and then add it. Reinforcement learning is another type of machine learning that actually also is sort of creating this sort of loophole, which is less deployed within the medical and medicine of artificial intelligence. However, it has similar sort of connotations as far as transformation of learning and reinforcement of learning through different sources. So these are the two things that we are also seeing a lot that is being happening. Of course, I think that's not possible to use ImageNet for artificial intelligence in medicine, but Google does not think so. They actually did take out a paper in which they actually said that if you use just ImageNet, to be honest with you, according to them, good enough, because if you really do lightweight CNN models, it is actually of equal accuracy. Of course, we are not doing lightweight equal accuracy. This is not comparing apples to apples, but interestingly, there are people out there who think that we can use truly transfer learning from other natural images as compared to medical images and use that learning into medicine. I wouldn't recommend that. I'm not saying you that it should be done. What I'm telling you, again, that transfer learning is one of those processes that are being increasingly used. Given that we have trained one model, why not use the learning from that model to apply to another set of data set, because we have insufficient data, less data, etc. Now, the second big trend that is going towards artificial intelligence is MLOps, and operationalizing of machine learning projects. Look, there's a big myth in the medicine community that if you're going to give more data to this particular project, that's going to improve the prediction moving forward. That's not true. There's not a single, let me repeat that, there's not a single FDA-approved artificial intelligence algorithm that does continual learning. Period. Not that I know of, and these are all referenced onto the blog as well. The issue really is that if you have this, what you really want to do, what is the holy grail, is that there's a continuous integration, there's continuous training, and there's continuous delivery. You actually have, integration of new data that goes into the training, and then you spit out with a new model and goes into it. That is truly the holy grail, but that is not happening at the moment. We are moving toward machine learning operationalization, MLOps in health. And where we're going to go there, I'm going to tell you in a minute. The real issue comes in because we have data shift and model shift, and we need to account for that, right? That's what happens with the sepsis. Epic is the largest electronic medical records management company in the world, and they developed this algorithm to figure out if their patient has sepsis or not. And external validations thought that, oh my God, this sucks. This was completely idiotic. And as a matter of fact, they had to apologize. And the reason behind that, they said, was because of the COVID. The sepsis that happened in the COVID patients are completely different. And the way the models were developed was before COVID. And therefore, if you're going to apply to a different population, data shift, then you're not going to have the prediction that you're looking for. So that's why there's continual learning, especially in FDA-approved products, is not being done, because we cannot account for data shift in a perfect way. What we have to do is basically always account for data shift. This was a paper published in New England Journal of Medicine, extremely important paper to read to understand what are the different types of data shifts, where it can move, and therefore it's referenced again into my talk as well. So what you're looking for is a design process in which the engineering in itself is looking at the model development and a constant cycle of model development, and then operations, and then making sure that those operations are also constantly recycling new source of data, new source of learning, and new sources of delivery. So you have to make sure that they are moving towards it. Now, where does it apply? Unfortunately, I have not seen personally applying into machine learning in medicine, in clinical medicine, but it is applied in healthcare all over. Believe it or not, it is everywhere. All billing is done, as far as insurance billing is concerned, is going through some sort of artificial intelligence, and that is basically operationalized. And at least in the United States, where we're looking at the business of healthcare, is one of the places, especially in terms of ICU stays, in terms of hospital stays, in terms of decreasing ICU length of stay, in terms of decreasing transfers. All of this, the business of medicine, is being operationalized and is done over artificial intelligence. Epic has a business intelligence portal completely that looks at all of these things and have all these predictions being done. And we'll see that coming into the artificial intelligence. As a matter of fact, I've spoken about convergence of virtual care and artificial intelligence, where virtual care is going to become a continuum from telemedicine, telehealth, to basically a complete global digital health solution in which AI experience data will be inbuilt, and how artificial intelligence will plug in play in terms of everything from radiomics, genomics, provider, clinical services, paraclinical services, etc. So we're seeing that shift moving forward, but at this moment in time, we do not, again, have any operationalization in direct clinical world, but for non-clinical healthcare business world, MLOps is standard. This is another animation that actually shows a different clinical pathways, how operationalization would really work if it were to be implemented. Now, the other last thing important is understanding the multimodal data nature of the medicine itself. Look, the data in medicine is not longitudinal, just one phase. It is actually longitudinally over time, and it is multimodal in terms of imaging, genetics, analytics, etc. So what we are really truly moving towards is multimodal data, and which is important because of the diseases that we are actually encountering right now. We're not able to find, let's say, biomarkers. So if I have to predict who has Alzheimer's or not, there's no troponin for it. Oh my God, that would be so amazing. We can get a troponin test, but we can't. So what we need to do is we need to find better predictive markers, because the minute we find better predictive markers, then we can put them into clinical trials and actually stop Alzheimer's disease. But if we find them so many late, no matter what medication I'm going to do, the brain has atrophied. So in these kind of situations, we really need the multimodal data to actually predict it, because we don't have troponin. If we had troponin, that would be not an issue. So now what we do is we basically have imaging data, genetic data, and clinical data, and they're processed into all of these different features, and each one of them has feature extraction, and then these feature extracted features are then into immediate features, and then they go into decision level tree, and therefore we are able to have a true predictive way of finding out who actually has Alzheimer's. And this is where the industry is moving towards multimodal data usage as far as medicine is concerned. So we're seeing a lot of examples, and especially in neurology, as I suggested, is being used, and another one is epilepsy. Now, another big concern in the industry, especially in the medicine is concerned, is about privacy and collaboration. So let me go into that one. So for example, what we had was normally, like, for example, I have a database of 10,000 echocardiograms of the heart or CT scans, and I actually put it on my laptop and let the data actually go into different situations, and then somebody else is doing it. This is considered local learning. But that's not the best way, right? I mean, we need more and more and more massive amount of data. So what we do is we pool all the data into a central location and a central repository, and then from there, then you actually train the data. This has a massive implications of privacy, because all the data will be mixed in, and somebody can steal it, and others can use it, and somebody can actually sell it. So therefore, there's a significant issue of privacy. And then, of course, there are other issues from cross-country collaboration is concerned, because let's say if I have FDA approval, but I want to check that study to Italian population, or I have to study the same population in Malaysian or Pakistani population, what am I going to do about it? So this actually creates a bottleneck for both privacy and collaboration. So there are two things, federated learning and swarm learning. Those are the two different ways in which we are actually able to circumvent that to increase privacy and increase collaboration. So what we do is, so rather than actually continuous learning, central learning, in which we push all the data into one location, what we do is we keep the data at the out edges. We never bring the data in, or if you bring it, we bring it in a way that is actually the learning. So this learning that is actually is pushed into it, and then the learning is compared, and then that learning is actually changed and then revamped and then sent back for further training and back and forth. So data always remains at the edge, but the learning becomes centralized. In swarm learning, it actually takes it to the next level. It doesn't only take the learning, the actual learning remains in the central point because of the data is actually out there. What it does is that it actually even pushes out the learning at the edge itself. So data and learning goes back, but the core learning in the terms of prediction, it comes back and confirms with each other that are we in sync or are we not, and therefore recommends that, okay, this is something that we need to explore either on a generalized model basis or a specific population basis, because this could be different population data as well. So these are the two ways, the federated and the swarm learning, in which we are protecting data privacy, and also we are protecting learning models itself, because some of these models again can be proprietary. One company is doing this, another company is doing this. How do you compare those models in a proprietary level as well? You can do that from swarm learning as well. So this is another way that the industry is moving towards federated learning. If you look at the general industry, Google is going to change the way it actually does advertising to federated learning, right? Completely. It's going to change it within a year or so, and it's not going to have individualized data points because of privacy concern. So that's what we are moving towards by protecting collaboration and privacy, and you're going to see more and more studies that are going to include federated learning and swarm learning as far as AI is concerned. Now look, artificial in neurology has been important, and the publications per year have been increasing. In 2018 and 19 was 77 and 70. 2020 was 172. It's more than doubled. We are seeing a significant amount of increased artificial intelligence as far as being published in medicine in general and in neurology in particular. If you look at the overall data as far as different subspecialties are concerned, critical care, dermatology are still lower. Cardiology, COVID-19, of course, is clearly one of those places where you see a highest amount of publications, and then neurology is on par with them. The number of publications, if you look at in the last 10 years, interestingly, have been in Alzheimer's disease and Parkinson's disease. The reason Alzheimer's disease is because there was a lot of data that has already been collected in a systemic fashion. There has been a lot of research that has been going on. So putting that whole data into an artificial intelligence study, again, the minute you have data, you can have any kind of study done, right? So that was one of the reasons that artificial intelligence, same thing with dementia and Parkinson's disease, was variables and different multimodal data to predict dementia and other, modalities. So therefore, you could see about 50% of it is related to dementia itself. Then comes epilepsy. Autism, again, has major implications as far as treating it, and able to predict it would be a huge impact on social benefit. So there are the places that we're looking at. Unfortunately, stroke, MS, etc. have not been academically active. Interestingly, commercially, at least in US, stroke is the only one, right? Because that's the only one that is paid through CMS. That is the only one that is being used on a consistent basis everywhere. But the academic places are distributed in that fashion. Now, what I'm going to do is the last of it, I'm going to let Adil talk, and then I'm going to put the rest of it into the web. And what I'm going to do is we're going to basically have computer vision, neuroradiology, digital pathology, other kinds of computer vision application. I'm going to give one example each, then go to natural language processing, in which I'm going to talk about chatbots, EMR summaries, and how that's, and then Adil is going to most importantly talk about signal processing and how he's doing multimodal data in his machine learning project. Again, I'm very grateful for your time, and thank you for being here.
Assalamu alaikum, everyone. And thank you so much to Dr. Junaid for a lovely introduction to machine learning. My job in the next 15 minutes is to share with you all a practical application on how we can use signal processing to acquire a data. And once we have acquired data, how we can use this information in a neurological disorder. For this presentation, I will be sharing some of my ongoing thesis work in neuroengineering. And before we get started, I would briefly introduce myself. My name is Adil Maiman. I am a Dow graduate, class of 2013. I finished my neurology residency training at the University of Alabama at Birmingham. And then after my residency, I stayed in the same program for a hybrid fellowship after securing a trainee award from the NIH, NINDS, which is allowing me to pursue a clinical movement disorder fellowship, as well as a PhD graduate degree in neuroengineering. Thank you so much to the Pakistan Society of Neurology for providing this platform so that I can share with you all some of my ongoing thesis work on quantitative sleep neurophysiology and cognition in Parkinson's disease. So before I begin my presentation, I would like to share with you all our next 10 years goal, which is to address the most challenging question frequently encountered in today's movement disorders clinic, asked by Parkinson's disease patient. So that is, when am I going to develop dementia, which will ultimately take me away from my family to a nursing home? And is there anything that you can do to either prevent or delay this inevitable future? Now, with a deep interest in neurophysiology, our hope is to come up with some useful electrophysiological markers that will help us to predict dementia risk in Parkinson's disease patient and ultimately work towards develop therapeutic options to delay its progression. So this brings us to the objectives of this talk, which could easily be summed up by following the title of this presentation. First, I will talk to you guys about why is it important to study cognitive disorders in Parkinson's disease. Following that, I will discuss why it is important to study quantitative sleep EEG markers in Parkinson's disease patient. And lastly, I will tie everything together and talk to you guys about the role of sleep quantitative EEG markers in Parkinson's disease cognition. I will finish my presentation by giving future directions. So in order to better appreciate the importance of cognitive decline in Parkinson's disease, we will have to go back to 1800, particularly 1817, when Dr. James Parkinson first wrote the clinical description of Parkinson's disease in his essay on the shaking palsy, where he completely ignored the cognitive decline in Parkinson's disease and described absences of any injury to the senses and to the intellect. It took the field almost 50 years to first emphasize on the importance of cognitive decline in Parkinson's disease, and it was first done by Charcot in 1877 when he said, at a given time, the mind becomes clouded and the memory is lost. Following that, several other accounts of information on Parkinson's disease dementia also emerged around the same time. So Ball in 1882, Parent in 1883, and Compton in 1902. Yet despite these great observations, the importance of cognitive decline in Parkinson's disease was often minimized as an accessory to the normal aging process rather than an integral part of the disease. Now, this disparity in thinking that Parkinson's disease is just a movement disorder without giving much importance to cognitive decline could easily be reflected in today's movement disorders clinic. And just to reiterate this point, I will read a quote from a Parkinson's disease patient, which was published in a report from a multidisciplinary symposium on unmet needs and future directions to maintain cognitive health by Dr. Jennifer Goldman in 2018. A patient said, I wish that the doctor had told me that cognitive changes could be one of the results of the disease. My clinic visits have focused much more on the physical signs and symptoms. The few times cognition has been addressed, the comments were very brief. Now in 2021, if somebody is diagnosed with Parkinson's disease dementia, guess how many pharmacological treatment do we have? Only one, rivastigmine, which we all know is cholinesterase inhibitors, comes with a lot of side effect and doesn't even slow down the progression of the cognitive decline. And if someone is diagnosed with mild cognitive impairment, unfortunately, we do not have any treatment or therapeutic options for that. One of the reasons why it is so difficult to develop a therapeutic target or therapeutic options for cognitive dysfunction in Parkinson's disease is because of its heterogeneous nature. It frequently involves deficits in executive function, working memory, attention, visuospatial function, processing speed, and language. Now, this figure over here shows three main neurotransmitters which are thought to be involved in cognitive dysfunction in Parkinson's disease. So mainly they are dopaminergic neurons, which produces dopamine neurotransmitter and is thought to affect the executive function. Acetylcholine, which thought to affect the memory, learning, and attention. And norepinephrine overall affects the cognitive dysfunction in Parkinson's disease, but it's not entirely sure which domain it affects the most. Now, one of the exciting ways to study cognitive decline in normal, healthy adults is through the microarchitecture of quantitative sleep EEG. Now, this area is largely unexplored in Parkinson's disease. Now, these neuromarkers are recorded by measuring the brain waves through the scalp EEG during a sleep study. We typically use 6 electrodes, so 2 in the front, 2 in the middle, and 2 in the back. And also during a sleep study, one can also record eye movement activities, heart rhythm activity, and muscle activity through the EOG, ECG, and EMG leads, respectively, and also the oxygen saturation, respiratory volume, and respiratory effort to diagnose other sleep disorders such as sleep apnea. Now, this figure over here basically shows the main stages of sleep, which are divided into rapid eye movement and non-rapid eye movement. Within the non-rapid eye movement, it is further subdivided into stage N1, N2, and N3, and it is based on the brain wave activity. So during the awake time, the brain resonates predominantly in the alpha rhythm, which has a frequency range of 8 to 12 hertz. During the stage N1, theta waves are predominated, which has a frequency range of 4 to 8 hertz. Stage N2 is characterized by sleep spindles, which has a frequency range of 9 to 15 hertz, and also the K complexes. And stage N3, which is also called the slow wave sleep, is predominated by greater than 20% of the delta waves, which has a frequency range of 0.5 to 4 hertz. And lastly, the rapid eye movement, which has a mixture of frequency, but the predominant frequency is the theta waves. Now, this blue line over here basically shows the transition into different sleep staging throughout the night. And this is also called the hypnogram. Another good thing that I really like about this figure is that it shows the normal physiology of the sleep. So it is predominated by stage N3, or the slow wave sleep, during the first half of the night, and then by the rapid eye movement during the later half of the night. So for this talk, we will be particularly paying attention to the slow wave sleep, or the delta spectral power during the stage N3. The reason why we chose to first study the slow wave sleep is because it serves as a proxy of neuroplasticity, which we all know is important in learning and memory. In the general population, sleep impairment increases the risk for dementia, particularly the slow wave sleep, which has a frequency range again of 0.5 to 4 hertz, is thought to be important for cognition and learning. They typically originate from the frontal cortex in humans. I will only be showing you the data from the frontal lead. We also know that the slow wave sleep is decreased in persons with Parkinson's disease. However, how does this decrease in slow wave sleep impact cognition in Parkinson's disease is largely unknown. And this is the goal of today's presentation. So in the next 2 slides, I will show you the schematic of our experimental setup. So all the Parkinson's disease participants underwent a sleep study where we recorded their brainwave activity through the scalp EEG. Once they completed the sleep study in the morning, our sleep specialist, in our case, Dr. Amy Amara, performed the sleep staging and converted all the EEG files into the EDF file. In the pre-processing step, I uploaded the EDF files into the MATLAB files and marked all the movement and the electrical artifacts so that I can exclude them from the final analysis. As you can assume that this was the most time-consuming step in our study. In the post-processing step, we perform signal processing in both the non-rapid eye movement sleep stage and the rapid eye movement sleep stage. So far, I've only completed delta waves spectral power analysis, which I will be showing you in this presentation. But of course, the goal of my thesis is to also look at other quantitative sleep EEG markers, which includes delta waves morphology, which is further consists of the slope and the amplitude, and then the number. sleep spindle spectral power and its morphology, and the functional coupling between the slow oscillation and the sleep spindle. And within the rapid eye movement, we are only interested in looking into the spectral powers. So along with the sleep study, the patient also underwent level 2 comprehensive neuropsychological testing, during which we evaluated their memory and also their cognitive functions in different domains. So what we did was we converted the raw scores in individual tests into the z-scores. Then we averaged all the z-scores together to obtain the domain scores. And then we average all the domain scores together to obtain a cognitive composite score, which was our primary outcome in this study. So in our study, we had 32 Parkinson's disease patients. They had mild to moderate Parkinson's disease. 60% of those 32 PD patients were male, 40% were female. This key over here again shows the different substaging of the non-rapid eye movement sleep stage. Again, N1 is dominated by alpha waves, N2 is by theta waves, and N3 is by the delta waves, also called the slow wave sleep, and this is what we are particularly interested in. This figure over here shows a correlation between the N3 delta power in the frontal lead, which is shown in the y-axis. Again, we were interested in just evaluating the frontal lead because the slow waves typically originate from the frontal cortex. And on the x-axis, we have plotted the cognitive composite score. As you can see that the N3 delta power in the frontal lead was positively and significantly positively correlated with the cognitive composite score, with a correlation coefficient of 0.39 and a p-value of 0.032. This significant relationship was driven by executive functioning and processing speed. In this slide, I'm showing you guys spectrograms from two participants. So this participant had a higher N3 delta power and a higher cognitive scores, and this participant had a lower N3 delta power and a decreased cognitive score. Think of a spectrogram as a way of showing descriptive statistics in a big data set. So on the x-axis, we have plotted the duration of the sleep study in hours. So it goes from 0 to 7 hours, and this is after the artifact rejection. And on the y-axis, we have plotted the frequency in hertz, which goes from 0 to 14 hertz. We limit it to 14 hertz because we are mostly interested in the slow wave sleep or the delta waves. The color inside the spectrogram basically represents the power within a certain frequency range. So the hotter the color is, the higher the power is in that frequency band. And this black line over here shows the transition into different sleep staging. And again, this is called the hypnogram. So as you can see that the patient was awake during this period, transition to N1, then N2, N3, and then to the rapid eye movement sleep stage. So as you can see that this participant had a higher N3 delta power and a higher cognitive scores as compared to this participant, which had a lower N3 delta power and a decreased cognitive scores. So what I've shown you so far is that delta spectral power during the N3 was correlated with the global cognition in Parkinson's disease. Although it is a novel finding, but it is not unexpected because we all know that the slow wave sleep is important for neural synchrony, synaptic plasticity, and cortical reorganization. So my future direction is again to evaluate other quantitative EEG sleep neurophysiological markers and find their association with the cognitive or cognition in Parkinson's disease, and then determine whether these markers can predict the cognitive outcomes in a longitudinal study when we will follow this patient for 3 to 4 years. And then ultimately, we will try to evaluate the effects of treatments on these markers. And then I'm also thinking to perform some experiments by modulating the circuits through the deep brain stimulation or transcranial direct current stimulation or focus ultrasound to be able to perform the block and mimic experiment so that I can establish the causality relationship between the slow wave sleep and cognition in Parkinson's disease. These are my acknowledgements. Thank you so much again to Pakistan Society of Neurology for giving me this platform to share my data. And thank you everyone for paying attention. Thank you.
If you save a life, it is as if you saved the life of mankind. Please make sure you like, comment, share, and subscribe to my YouTube channel and my newsletter. If you want to get in touch with me, the best way is to go through Twitter or via LinkedIn. Also, make sure you follow the Academy website for regular updates. Thank you so much.